Thank you very much. Thank you to the organizer for having me speak here. I've been here already for one of the other workshops a few weeks ago, but so it's nice to be back, and also the set of people is somewhat different. So I decided to give a talk about this result. This was a long-standing project that was completed just a few months ago. We started with Antonio Montalbán, who is mentioned there, this project in 2019, actually, before COVID. It's another year, basically. Then, well, obviously, we didn't work continuously on that, also because there are 9 hours of time difference between me and him. And then I went back to California a few other times. We tried to progress. Then eventually we ran into problems. We decided how to solve them. Then we involved my graduate student, Andrea Volpi, in actually finishing off the whole thing. And Andrea was very helpful in doing so. So basically, we have completed the project, as I said, just a few months ago. So let's start from, well, this is a short overview. So I'll just recall some classical Ramsey theorems, and then how they interact with various largeness notions, which are something that has emerged in proof theory, it's connected with proof theory and with other notions. And then there are also barriers. Those of you who are familiar with the BQO theory know are those barriers, basically. So I will get back also to those. And then eventually I will put all of this together with what we call the barrier-Ramsey theorem eventually. Okay, so classical Ramsey theorem, well, this is just to remind you of the arrow notation. I assume most people are quite familiar with that. This is just the notation that, you know, it can be very useful in expressing in a concise way the content of the finite Ramsey theorem. So you use that arrow notation in red if for every set with n elements and every coloring of p tuples of those set with k many colors, p and k appear on the right, you will always be able to find a homogeneous set with m elements. And homogeneous means that all tuples from that set are colored exactly in the same way. And obviously, so with this notation, Ramsey classic theorem, the finite case, can be stated that given m, p, and k, you can always find an n, there is an n large enough so that the arrow notation works. And the Ramsey number is just defined as the least n that works, because obviously when some n work, also larger n's will work. And this is notoriously a difficult numbers to compute, well, except some very basic cases, right? R322 is the basic game that you are in a, you know, at a party with six people, either you know either there are 3 persons that know each other beforehand, or 3 people who don't know each other beforehand, so that's 322. Then there are a few other results, R4 to 2, R3 to 3, but Ramsey numbers are very difficult to compute. For example, for R5 to 2, we have those bounds, 43 and 48, and there has been no progress in recent years in closing that gap, right? And for example, a few years ago, Sa proved this estimation, this upper bound on the Ramsey number, and this was, you know, celebrated as a major achievement, a major step forward in having bounds for these Ramsey numbers. So these are very difficult. I will show you, my hope is to get you convinced that when you get to the transfinite appropriately, then this, we can compute some of these numbers, basically, which is quite surprising, given that in the finite case, they are notoriously difficult to compute.
Sorry, can you show the...
Yep. Okay. So P on the top is the size of the tuples. The K below is the number of colors. That's maybe the thing that can, you know, leave somebody perplexed. I think that's standard notation. I mean.
I was just wondering what order.
In that one. Okay, well. All right. So then there is the infinite Ramsey theorem, also due to Ramsey, obviously, which is the case where if you get it into the infinite case, somehow everything becomes simpler, because you don't have for every m to have an n, but actually aleph naught, let's say, or omega, will work in both cases. If you have an infinite set and you color the p tuples of that set with k many colors, you will find a homogeneous set with omega many colors. And also notice that from the infinite Ramsey theorem, by a quite simple compactness argument, you can get the finite Ramsey theorem. It's something that is actually well known. I mean, here I'm just reviewing quite thin. But also note that this kind of proof is a proof by contradiction. Assume that there is a counterexample for any n, and then you put them all together, you piece them all together using compactness, and you get a counterexample to the infinite Ramsey theorem. So this kind of approach yields no bounds whatsoever on the Ramsey numbers. All right, then comes largeness notations. So this is a notion, well, I don't know if exactly it was introduced by Paris Harrington, but was surely used by Paris Harrington in very important result. A finite set is large if it has at least one more element than its minimum element, right? I mean, you could also say greater than or equal, but then you run into troubles with zero, so let's do at least one more. And this is the notion of a large set. So the large set depends not only on the size, but also on its elements, in particular on its least element. And Paris Harrington showed that if you fix M, P, and K, you will again be able to find an N such that for every coloring of NP with K many colors, there exists a homogeneous set of cardinality at least M, but also which is large in the sense of the definition. Obviously, this is not the main result of Paris Harrington. The main result of Paris Harrington is contained in the last line, so that this statement is actually not provable in PA, although it's a perfectly sensible statement of finite mathematics, finite combinatorics, so that was the import of that result. But this is also the idea that you can look at Ramsey theorem by looking at notions of largeness which are different or more general than just a mere size, let's say. So that's our starting point in this sense. And again, you can get the first part, the part of the existence of n, from the infinite Ramsey theorem, again by the same argument. And if you realize what we are doing, you are using that any infinite subset of n will have an initial segment of size at least m, because you want also that m, and which is also large. So basically, this notion of largeness is such that in any infinite set, there is an initial segment. So I'm just thinking of sets here as enumerated, sets of natural numbers as enumerated in increasing order, just that is large, you know. So that's what is important in this largeness notion, right? To run the argument. And whenever we have this, we can basically run the same argument. And then obviously the other part is saying that this n will grow very fast as a function of m and p, and so can be restated as that we need infinitary means to prove this finitary statement, and this is mathematical content of this result. But I'm not going to explore that anymore. No, I don't. Not many. So these bounds I mentioned, I mean, here. Okay, there is actually on the Electronic Journal of Combinatorics, there is a paper which is updated from time to time. Actually, now it's a few years where it hasn't been updated, which, you know, keeps track of different Ramsey numbers. Also, when you have different, you know, you color with two colors and you want either a set of two elements of three elements of this color or sets of 15 elements of whatever colors, things like that. So asymmetric Ramsey numbers, there are all sorts of things. So they keep that updated, but I don't think they have anything about Paris Harrington there. This is, you know, sort of combinatorial stuff, right?
Can you fix
the number of, I think it suffices to colors, but maybe there are other people who are, you know, more experts. Yeah, it's the exponent, but yeah. And then shortly, actually, after Paris and Harrington, Ketonen generalized the notion of large sets which we were using in Paris Harrington by defining the notion of a finite set to be alpha large for any alpha actually up to and included epsilon naught. And which is, well, I just recall the least fixed point for the ordinal exponentiation. And this is done in such a way that m large means size at least m, omega large means large in Paris-Harrington sense, and you can move forward and get to larger ordinals. And we will be working in this sort of idea, I mean, but hopefully going beyond epsilon naught also. And moreover, what is again crucial, and I'm underlying here, is that these notions of largeness has these true properties. If you take any infinite subset of a natural number, you will find an initial segment of that set, an initial part of that set, which is going to be alpha large. And also, well, something which is maybe sometimes is not underlined because it's, you know, if you use the word large, it's obviously that something which is larger than something that is large will still be large. But this is something you need to take care of, please.
Large means that like
I'm going to give definition. This is just sort of a historical overview from the time. I'll give definitions. And to give a definition of alpha large, also already Ketonen, you need to use systems of fundamental sequences. So I need to have a slide on that. A fundamental sequence for an ordinal greater than 0 is a non-decreasing sequence of ordinals which go up to alpha, well, with the +1 to take care of the successor case in an appropriate way, basically. And also we let for convenience 0, we attach a fundamental sequence also to 0, which doesn't make sense in some, because you have no ordinal smaller than 0, but just set that 0, 0, 0 is the fundamental sequence for 0. And then it's obvious that for every alpha greater than 0, alpha n should be smaller than alpha, so you get a smaller ordinal. If we fix a countable, an ordinal, well, countable in this, yes, countable because we need everything to have a countable cofinality. A countable ordinal gamma, and for any fundamental sequence for every alpha less than or equal to gamma, we obtain what we call a system of fundamental sequences on gamma, right? So for example, Ketonen started from a system of fundamental sequences on epsilon 0 in this sense, but here I'm giving a more general definition. So if you are given a system of fundamental sequences on gamma, here is the definition of alpha large. So what you take a set A, and you can start from alpha, because you want to check whether A is alpha large. You apply alpha to the first element of A, the minimum of A, and you will obtain a smaller ordinal. Then you have a system also for the smaller ordinal, and you will apply the second element in A, and blah, 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 and go on and so forth. And here you obtain a strictly decreasing sequence of ordinals unless you hit 0, basically, right? If you hit 0, then you are stuck at 0. But if you don't hit 0, you are always going down. And so you can define A to be alpha large if using the set A, you actually get to 0. And that's the notion of alpha largeness. And then we also say that A is alpha size. This is maybe slightly less standard notation. If it is alpha large, but barely, I mean, you just get to 0 at the very last step. If you had just one less element in A, you are not getting to 0, you are not alpha large. So just the right size to be alpha large. And and then observe that if you start from an infinite set, then a finite initial segment of X will be alpha size, just because there are no strictly decreasing sequences of ordinals. So deep here, but it's a key observation here. You can also define equivalently the notion of alpha largeness in another way. You say, well, every finite subset of natural numbers is actually 0 large if you start from 0, and then you go by recursion. Well, you want to say that the empty set is not alpha large for any alpha larger than 0, because the empty set is the smaller set, actually, right? And then if A is non-empty, then A is alpha large if and only if, when we take off the least element, it is alpha of that element large in that sequence. And so it just mimics in another way the previous definition, I mean, just going from by recursion. So there are two equivalent definitions of alpha large here. And well, if you want to go, for example, with a system of fundamental sequences up to omega, which is just the easiest thing to do, I mean, the toy case, well, basically, probably you will define m plus 1 of n to be m, and omega n to be n for any n. This is the obvious choices, unless you want to do something more complicated or strange. And then m large means exactly that A has exactly m elements, and omega large means exactly large, as in Paris Harrington. And so we are exactly recovering those notions as we were expecting. Now, in working with this, we realized that we need to have some properties of these systems of fundamental sequences which will work. So one property is regularity, and here you write an ordinal smaller than gamma in Cantor normal form, basically, so that omega to the beta 0 is the first coefficient in the Cantor normal form in base omega, obviously, which means that beta 1, what the remainder must be smaller than omega to the beta 0 plus 1, actually. And then in this case, if you want to compute the sequence for, here it is, the sequence for this ordinal, which is the sum in this way, then you actually forget about the first part, or you keep it as it is, and you apply it to beta 1, as long as beta 1 is greater than 0. So actually there is a second addend in this sum. What? Which inequality? No, we want this to be exactly like that, yes. For our purposes, at least, it's what it works, it's what is more natural to do. And then we have this other notion, which is a notion we call nestedness. Basically, you don't want a fundamental sequence for beta and a fundamental sequence for gamma to be interlocked in some way. So we don't want this ever to happen. For the same n, we don't want that beta n is already going down below gamma, but then gamma n is going below beta n, so something like that. This is actually a weakening of another property which is in the literature, the so-called Bachmann property. There is also a recent paper by David and Andreas actually about this. And in this case here, instead of n, you put always 1. So this is weaker than asking that this never happens, is weaker than asking that this never happens. And it occurs that for the system we have nestedness, but not the Bachmann property. So we are, we need that. I mean, and we show that this is enough for our purposes. And so the idea is that if we define alpha largeness using a nested system of fundamental sequence, we have also that other property that I already underlined before, that a superset of an alpha large set is also alpha large. And here nestedness is essential for showing this. Okay, well, then going a little bit beyond the toy example of a system of fundamental sequences for omega, let's go to epsilon naught. This is already what Ketonen was doing. So for our purposes, we take this system of fundamental sequences. Condition 2 is just saying basically the regularity. And then a condition 3 is quite natural. I mean, when you have something of a form omega to the alpha. And for epsilon 0, we take the fundamental sequence, the natural one, when you explain what epsilon 0 is, right? You just iterate exponentiation. And so the nth element will be the having iterated exponentiation exactly n times. And if you do this, this is regular and nested in my sense before, and so everything works. And using a system, this system, or just slight variants of this, now one should look at, several people proved several theorems already about extension of Paris Harrington. For example, Ketonen and Solova in 1981. So they proved this arrow notation here, when this notation here means a tower of n omega powers with beta on top. In this case, beta is k plus 6. So they were looking for omega large homogeneous sets. So this is like a sharpening of Paris Harrington. I mean, computing exactly how much large should be the initial set to be there. And in some sense, maybe this is the answer to the question you were asking.
Well, I was asking about the
finite. Well, okay, because this is everything is finite, right? This is a notion of largeness for finite sets. In any case, it's represented by an infinite ordinal, but it's a notion of largeness for finite sets. So there, the size of a set was instrumental in Paris Harrington to avoid trivialities or something like that, because otherwise you could just play with very small sets. But what is essential is that here you need this large set. I mean, because here you want a large homogeneous set, the omega, and so here you need a large set in some appropriate sense as a set where you put the coloring. Make myself understood. Andreas maybe can. This is what it means. I mean, just to get familiar, to get on the same page with this.
Oh, that's the different use of the arrow.
Well, and it's saying that this is a set which is this large, right? This is always finite Ramsey theory, right? Except for my appeal to the infinite Ramsey theorem to prove some finite results. Otherwise, I'm doing finite Ramsey theorem all around. Okay? So you don't have to think like I'm coloring this ordinal, but I'm coloring sets which are large according to this ordinal. And here I'm looking for sets which are large according to omega large, so large in Paris Harrington sense. So this was a sharpening of Paris Harrington to say exactly how large was the set that you needed to start with, right? And so here I'm coloring this omega large, this omega p minus 1k plus 6 large set, which I call A, which has at least 3 elements to avoid trivialities, or yes, the minimum is at least 3, and so it would be much larger. And I color all subsets of size p of this at A with k many colors, and I can always find an homogeneous set which is omega large, homogeneous for C, and also that at least p plus 1 elements. This is something to avoid trivialities also, because if a set has less than or equal p elements, then obviously it's homogeneous just because either it's coloring only one p tuple or even no p tuple whatsoever, but you are not interested in any homogeneous set like that. I mean, at least p plus 1 is needed there. So that's their statement from 1981.
But they're not claiming that.
This is sharp.
Yeah.
I don't think so. This was sort of an upper bound.
Sharp somehow.
Or an upper bound. And then also, you know, this line of research goes on here. Probably it's not complete, but just to give you an idea, Bigorashka and Kotlarski gave explicitly also lower bounds for this. And here they were putting already ordinals larger than omega, always to be read as beta large. I want a beta large homogeneous set, and then I need an alpha large, and they have lower bounds here, right? So they show that for some alpha it's not enough. I mean, you need more than this notion of alpha largeness to get a beta large homogeneous set. For that p tuples of size p and k many colors. And for example, Lejek, which I don't say the last name, but was here a few weeks ago, and Keita, which was also here, they proved this result as a step in some conservation result for RT22 in reverse mathematics and first order part of RT22. And this is a result that has been rediscovered and reproved with 25 plus years of delay. First Pudlak and Rodul and then Farmaki. Here is a case of infinite Ramsey theorem, okay? And what is new, which is different from here, if you notice here we have p, which is a natural number. Here we have even 2, which is a natural number. I hope you all agree. And here instead they are coloring omega size subsets of M, but M is infinite. So now the largeness notion is not only in looking at the homogeneous set, which is large, alpha large for some ordinal, not only in how large should be the set that I'm starting coloring, but also in the size of the tuples I'm coloring, basically. The tuples are not of a fixed size, but rather they are large. This is different, and we take also this idea from here. Even though here you have an infinite thing.
So omega size again means
omega large subsets. So here they are saying, okay, I take an infinite subset, and instead of coloring triples or quadruples or whatever, I color omega large sets, which might be, you know, of 2 elements if the first element is 1, but of size 101 if the first element is 100, right? And then I color this, and you can always find an infinite set. So you could write this now in this notation, where here on purpose I distinguish between the cardinal aleph naught and the ordinal omega, because there is size, like, you know, being infinite, so being of a size aleph naught in set theory sense, right? And here omega means that I'm coloring omega large sets. Okay, so that's what Pudlak and Rodul and Farmaki did. But this was the infinite case, and to the best of our knowledge, there was no case where here you were simultaneously using alpha large and beta large here, and maybe gamma large up top here. So we can do that. Basically, that's the idea of what we want to try to do. And also we need to go a little bit beyond epsilon naught. I mean, up to epsilon naught, the system of fundamental sequences is almost canonical, basically. I mean, you can find in the literature small variants, but basically there is not, I mean, it's natural to do one thing. If you want to go a little bit beyond, that's less natural and you have to think about it a little bit. So first of all, let me recall the Veblen hierarchy and get into gamma naught. So the Veblen hierarchy is a sequence of functions. Let's start with phi0, which is just exponentiation of the base omega. All these functions are so-called normal functions, so we'll have many fixed points. And so you can define phi beta of alpha to be the common fixed point of all the phi gammas which are below beta, at least when beta is larger than 0 here, and we take the alpha common fixed point. So 0 will be the first one. So with this notation, for example, phi 1, 0 will be just the first fixed point for the exponential, that is epsilon naught we were discussing before, right? And then phi 1, 1 will be the second fixed point, which is also called epsilon 1 and so on, but you go on beyond with many betas, and I rushed here. And then you get to this way you can get to the so-called Pfefferman-Schutter ordinal, gamma naught, which is the first ordinal, which is a sort of fixed point for the Veblen functions, right? For any alpha and beta which are smaller than gamma naught, phi beta alpha is still smaller than gamma naught, and at least one. And you can obtain it also as a super by iterating on, the indices basically. And it's also the least beta such that phi beta of 0 is equal beta. So it's another ordinal. Well, the workshop is on reverse mathematics. I'm not telling much about reverse mathematics, but at least epsilon naught is the proof theoretic of predicative analysis, in particular of ATR naught in reverse mathematics, in the reverse mathematics setup. So it's an important ordinal. And we defined a system of fundamental sequences of gamma naught. Some choices here are sort of a little bit, I wouldn't say arbitrary, but a little bit that can, why did you do that? Well, because this is exactly what we need for having everything working eventually. And so some things are pretty natural. I mean, 1n must be actually 0. Then here it's to have that condition of regularity, basically, as we were saying. And then we were keeping with the notation for omega to the alpha when alpha is not a fixed point for the exponential, obviously. And then we define this. Here we iterate n plus 1 times phi sub delta n. Delta n is smaller than delta if delta is greater than 0. And so this is something that we already know, and we apply this n plus 1 many times. And here we have to play a little bit of this trick. I mean, I don't want to get lost in details. I mean, the idea is that we can set up a system of fundamental sequences up to gamma naught. And for gamma naught, we do again the sort of obvious thing. I mean, just iterate. Actually, I decided just to say this, but this is much more flexible than it looks. It's not something about gamma naught. Actually, if we have a system of fundamental sequences which is nice enough up to some ordinal, let's say zeta, then we can set up this situation here for gamma sub zeta, which would be the zetath gamma number, let's say, gamma fixed point for all Veblen functions. So we can do a little bit more, but for the time being, it's best to just focus on gamma naught. And the system of fundamental sequences on gamma 0 is regular and nested, and these two statements here are sort of very different because regular is basically condition 2. Nested in our paper takes maybe 4 or 5 pages of checking all possibilities, Nested means that there are no two ordinals in a certain situation with their fundamental sequences, and you have to check all the possibilities. Well, you want to punish some student. I mean, somebody said once, have them read this sort of things. Several pages. I hope we got everything straight. So we are able. This is in an appendix of the paper because it's it would be too much to do it in the body of the paper. And okay, so what was our goal, at least originally, and then we had to modify a little bit. So I will tell you about that. Well, the idea is to deal with largeness notion first, which are associated to ordinal larger than epsilon naught, because most people that have worked at that were sort of stopped at epsilon naught, where there were this largeness notion which were quite regular. At the same time, so we wanted to use largeness notion simultaneously wherever it's possible. Wherever it's possible, it means that we are looking for some beta large set we want to know which alpha large in my notation. Some alpha large set, we want to know which kind of beta large set we need to have to get that homogeneous set, but also we are coloring gamma large sets. Eventually, the only thing that remains a natural number is the number of colors, because there is no apparent way of substituting the number of colors with any other notion, right? And so we fix an ordinal gamma. Typically will be gamma naught or this gamma sub zeta, which I was mentioned before, a regular and nested system of fundamental sequences up to gamma. And well, when B is a subset of N and gamma is one of these ordinals, we use this notation, which is just a natural extension of the usual notation for N tuples for the set of all gamma size subsets of B. And with this notation, if I have alpha, beta, and gamma, you see I have the arrow notation in this case, beta here, alpha here, gamma here. So this is the gamma large means that I'm coloring gamma large sets. I'm looking for a beta large homogeneous set, and I ask, no, for an alpha large, I'm sorry, homogeneous set, and I ask how large is this beta, and K is the number of colors. And so this arrow means that every beta large set B with mean B large enough to avoid trivialities, and every map which colors the gamma size subsets of B with K many colors, there exists an alpha large subset H included in B, which is homogeneous for C. And here I also make a change on the K because, well, if I fix alpha and gamma and beta, well, it means that this works no matter what's the number of colors, basically, as long as it's finite. Obviously, we cannot go to infinitely many colors. So that's the sort of notation we had in mind in our original setup. And then, well, every infinite subset of N contains an initial segment which is gamma large. We can view every finite gamma coloring. Gamma coloring means coloring of gamma size subsets of our set of an infinite set as a finite Klopen partition of a collection of its infinite subsets. So I can view this as a sort of case, not really of the infinite Ramsey theorem, but rather of the Klopen version of Galvin-Prickly. But still we get the infinitary version that we need. And from that, you get an infinite homogeneous set, which will have an alpha large subset as an initial segment, because every infinite set has that. So what I'm getting here is that we can run the compactness argument also here, using Galvin-Prickly rather than the infinite Ramsey, or Klopen Galvin-Prickly, let's say. And what we get is that whenever I fix alpha and gamma, I fix the number of colors, I will be able to find a beta that makes the arrow notation work. Exactly, I mean, it's sort of parallel to what we were doing to get the finite Ramsey theorem from the infinite Ramsey theorem. Homogeneous means that it takes just one color. All gamma subsets of that set will all be colored in the same way. No. Yeah. No, just like that, yes.
Can you not run into trouble?
Well, that means that in your set there will be no gamma size, gamma large sets of even cardinality, for example, or of odd cardinality. For example, for omega large, you can avoid that because if all your numbers are even, then all your large subsets will be of odd cardinality because of a +1, right? So you can escape because you don't have necessarily gamma large sets of every cardinality. I know what I mean. That's a classic counterexample for doing, some sort of generalization of Ramsey. But here you escape those. And then also, since you can take the soup of, you can fix alpha and gamma, and then look for every k, you can find a beta, and then you can also get this result here that there is a beta that works no matter what the number of colors you are using also. So that's the part where we move from the infinite case, just using Galvin-Prickly, to the finite case. But obviously, we are not happy with knowing that there is a beta. Obviously, the question here, how large are those beta, basically? That's the question we were asking. Here? Well, it's basically, well, you will find an infinite homogeneous set by Galvin-Pricri, right? And then that set will have an alpha large, I mean, in the, okay, so assume that there is no beta. For any beta, you will be able to find a counterexample, right? And then you piece them all together by building for larger sets, you know, a counterexample. Yeah, it works. So the question is, how large are those betas, depending on alpha and gamma, maybe on K, or just alpha and gamma in this other case. That was our original setup. And, well, we had ideas about this, we worked on this, we found some problems that seems to be very difficult to deal directly when you are fixed the system of fundamental sequence for ordinals above epsilon naught. And therefore, we found eventually our way out by expanding further the notion of largeness to include largest defined by barriers, which I'm going to introduce in a little while. So this is barriers are a combinatorial object, which are fundamental in the theory, for example, of better quasi-orders, and were introduced by Nash-Williams in the 1960s exactly for that purpose. So I have to do a digression on barriers now. So, well, I was already doing this, but from now on, really, I do it straight. I mean, any subset of natural numbers is just the same as the strictly increasing function which enumerates it, the principal function, so-called. So S of I is the I plus 1th element of S. And I use this square inclusion if the enumeration of S is a prefix of the enumeration of T. So really, there are just the first that many elements of T. While I use the subset, the usual subset, if S is a subset of T as a set, which maybe skips, I mean, the minimum could be larger, the minimum of S could be larger than T when S is just a subset of T, and then obviously the strict relation as usual. So let me introduce this slightly large first notion, which is the notion of a front. So this is a set of finite strict increasing sequence of natural numbers, which are identified with finite sets of natural numbers. This is a front if either contains only the empty set, or, well, the base of this, which is the set of numbers which are mentioned, which occur in some elements of B, is infinite. For any infinite subset of this base, you have a prefix which stays into the set B, and then any pair of elements in B is never one which is the prefix of the other. So the prefix in 2 is unique, actually. Well, for when B is the empty set, it's convenient to think this is the so-called degenerate front, and the base of B is the natural numbers. It's convenient to have also this one around, I mean, for technical reasons. A block is a non-degenerate front, so satisfying 1, 2, 3. And we can always, up to isomorphism, we can assume that the base of a block is actually the natural number, so we can always go back to that particular case. A few examples of blocks here. Well, obviously, the most natural one is take just the k-size subset of the natural numbers, which satisfy all 3 conditions. Slightly more interesting is something like this. To decide whether S is here, you look at the cardinality of S, should be the minimum of S, as 0 is actually the minimum because they are listed in increasing order, plus 1. So this is being exactly omega large, omega size, right? So the largeness notion of Paris and Harrington, basically. And this is called the Schreier barrier in barrier terminology. And otherwise, you can look instead of the first element to the second element. You get something a little bit more complicated because you have many sets starting, say, with 0, right? In this example here, the only set which has 0 as a minimum is singleton 0 because it has cardinality 1. Here you have many sets starting with 0. You have a 0, 1, but also 0, 2, 3, 0, 2, 4, and 0, 3, 4, 5, 0, 3, 4, 6, blah, 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 because the second element is telling you how large you can be. And then even more complicated, you can use the minimum not to tell you what's the size, but to tell you where to look for what's the size, basically. And you get more and more complicated stuff. So barriers can be quite complicated. That's the message of these few examples, basically. because a front is a barrier where instead of asking that two elements are incomparable with respect to prefix, you also ask that they are incomparable with respect to inclusion, which is a stronger condition. And so every barrier is a block, which is in turn a front. And then we have some sort of special barriers, which are called smooth barriers. This came back into my life when we started working on this, because I introduced this notion in my PhD thesis, which is quite long ago, for completely different purposes, but it seems that they were just right for doing this. I mean, so it's a sort of nice of closure of time or something. You know, maybe there is something, you know, in these relativistic models or something about that. So a smooth barrier is this very technical definition. If you have two elements of a barrier B and one is shorter than another one, it must be that on at least one coordinate it's actually strictly below it. And actually all examples that I gave in the previous slide are actually smooth barriers, but you can show that there exist blocks which are not barriers and barriers which are not smooth. You just build them on purpose, basically. Although the most natural barriers actually come out to be smooth. I mean, if you don't want to hurt yourself, you will come up with something like that. And why we are using smooth barriers? Well, even starting from B, which is just a front with base the natural numbers, we can say that something is B large, a set T is B large if there exists some prefix of T which actually is in B, is in the barrier. So the barrier is telling you when something is large, basically, or just the front. If it's B small, in case it's not the case, and B size is precisely that, and nothing is slightly smaller. So, for example, if you take the barrier of K tuples, the B large sets are exactly those of cardinality at least K, and otherwise you get, with Schreier barrier, you get exactly the sets large in the sense of Paris and Harrington. So we are still recovering everything, not losing anything here. If B is a block, then for any x, just by definition, basically, there is a prefix of x, any infinite x, there is a prefix of x, which is exactly B size. So exactly large and nothing better than that. And if B is a barrier and T is large, then also the superset condition is satisfied, which is not the case for blocks which are not barriers. So that's one reason for moving from blocks to barriers. We need barriers, otherwise you don't have this property. Then if B is a front, you can, again, the front are the most general, you can consider this tree, which is the trios of things which are either small or just a size. Exactly, this is a well-founded tree. And you can define the height of a well-founded tree as usual, basically. And if B is a smooth barrier and S is an element inside the tree, then the sequence of the height of the immediate successor of S into the tree are exactly a fundamental sequence for the ordinals you are looking at. So we are looking at a sort of system of fundamental sequences, but rather than attach it to a single ordinal, you attach it to the ordinal which is attached to this element S, which is inside the tree. And this works if exactly because the barrier is smooth. I mean, when the barrier is smooth, otherwise you might fail this. So this is the reason for having smooth barriers, because otherwise you can give counterexamples to this basic situation. So basically, we are sort of recovering systems of fundamental sequences with a little bit more freedom, because maybe the same ordinal is attached to different elements into this tree, and the sequence is attached, the fundamental sequences attached to that ordinal in the two situations are different. They need not be the same. So we call this a pseudo system of fundamental sequence on the ordinal, which is the height of that barrier. And we have a notation which also puts in evidence which is the node where we are looking at. Then we need a little bit more to mimic the decomposability of a system of fundamental sequences. If the regularity, if A and B are fronts, I define another front, A plus B, in this way. This is just concatenating an element of B with an element of A. It might seem strange that I write A plus B and then I put the element of B before the element of A. And then this condition is just that it makes sense to keep the concatenation strictly increasing. And the reason why I do it the reverse way is because I want this one, which is what I care, and it's much nicer. So, because ordinal sums works that way, right? So the height of A plus B is the height of A plus the height of B. And this again might fail if you don't have a smooth barrier, so we want smooth barriers here. So when I have a smooth barrier and the height of a smooth barrier is in Cantor normal form written as the sum, well, here the interesting case is where k is at least 1, so there is at least 2 summands in the Cantor normal form. Then we say that this barrier is decomposable if there exist smooth barriers that when you sum them, you get back exactly the barrier. So it breaks down according to the Cantor normal form in a nice way. That's basically the idea. And then we have some sort of interplay between fundamental sequences and barriers. In one direction, what we have, if you start from a system of fundamental sequences on gamma, and then for any alpha less than or equal to gamma, you can find the set B alpha, which is the size of sets which has exactly alpha size according to that system of fundamental sequences. And this turns out a block. If a system of fundamental sequences is nested and regular, so nice in my sense for the systems of fundamental sequences, then every B alpha will be nice as a barrier, so smooth and decomposable. So that's exactly what I want. I mean, that I'm taking under this barrier umbrella, let's say, also the things that were coming from systems of fundamental sequences, which were nice enough, let's say. In the other direction, what I have a smooth decomposable barrier. The height is written in this form, in Cantor normal form. There is a decomposition because it's decomposable. And then basically, you have something which is mimicking, in this case, the regularity, and in this case, the nestedness, but, well, not for, I cannot say for ordinals, because the system depends on the position, but in some sense, everything is pseudo nested and pseudo regular, let's say. And then I get to what we can do we can prove this barrier Ramsey theorem. It's just a few slides now. So basically, I have to introduce a arrow notation for barriers now. I started from natural numbers. I moved to ordinals when I had the largeness notion, and here I do it for barriers as well. So let A, B, and C be fronts. Well, for giving the definition, it suffices by be front. Then I will apply to smooth barriers. But if A and B and C are fronts, there is some interplay between the base. Basically, you can think that all have base in the natural numbers. And then what the arrow notation means that if I take a set S, which is of the size for this barrier, this is the barriers which is obtained from B by adding after each element of B maybe another singleton. And this is taking care of, mostly, well, the height of this is 1 plus the height of B. So it's just to making the infinite ordinal and the finite ordinal case match, basically. That's the reason for this thing. We need to this. Then we have a K coloring. K is still a natural number. It's the only thing that is still a natural number. And here I'm coloring the C size subsets of this set S. Then I can find a set. Here the set I want it to be C plus A large. The idea is again as before, that I want this set to have something of size C and possibly more than one set. Otherwise everything is homogeneous. So I want to make sure that the homogeneous set is large enough to accommodate many copies, many sets which are actually colored, so that saying that it's homogeneous makes sense, it's real requirement. So that's basically the idea of having C plus A, because anything like that has a C size plus something else, and so there will be many C size subsets, the initial segment plus others. And then this is homogeneous, so everything is of the same color. So this is my notation. And the infinite Ramsey theorem tells me again that, or maybe here I should say again Galvin-Prickly perhaps. Well, some infinitary form of Ramsey theorem to be on the safe side, that given K, A, and C as above, I can again find a B exactly as before. I can find a barrier which satisfies the arrow notation. So by itself, this is, I don't state it as a theorem because it's just an easy corollary of a well-known theorem, but our point is what we can say about the height of B given K, the height of A, the height of C. So if I know those ordinals and that natural number K, what can I say? And I can define the Ramsey number here for alpha, gamma, kappa, K to be the least beta such that all A smooth barriers with height A and all C smooth decomposable barrier with height C. I think here we could also add decomposable, but we don't use it. There exists a smooth barrier B with height of B equals beta and base B equals base A that works for the arrow notation. And so I can define some sort of Ramsey numbers also in this case. And moreover, I can define the sup when I move K and I get this Ramsey number less than omega. This is the sup of countable ordinal, so it's still a countable ordinal. It will be something that will work for any number of colors. And here I am. Well, I just need one thing to state. Well, it's 1 minute. It's the last slide. I just need something to state the result. I have to say what is this beta, basically, and I have to set up some notation. We set up this notation independently, and then I think Fedor actually pointed out that there was this previous paper by you, right, and Josten, which were defining in a more general setting what you call the hyperation. So in this setting, which is a special case, is exactly this. You take the ordinal gamma, you write it in Cantor normal form, all obviously exponents are weakly decreasing, right? And then you define a phi sub log gamma in our notation, like this. You take phi gamma naught, composed with phi gamma 1, blah, 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 composed with phi gamma k. These are the Veblen functions of indices gamma 0, gamma 1, etc. Notice that I have to do it in this way, because if I start, I mean, the rightmost is the first one I apply. If I add phi gamma naught on the right, then I will have a fixed point for all the others, and there would be nothing, or at least maybe some gamma naught more, but not more. And this way, I obtain this thing here. So this is what was called the hyperation in this context of the exponential with base omega. And then here is the main theorem. If in that system, if I take alpha and gamma smaller than or equal to gamma naught, and I can go a little bit farther, as I said a little bit before, and at least one of them is infinite, because otherwise I fall down in the finite Ramsey theorem, and it's a nightmare computing Ramsey numbers, right? So I want really to be in the infinite case. At least one of them must be infinite. Then the Ramsey number, here again, I have this one for matching the finite and infinite case. But basically what I do is I take alpha times omega, and then I apply this phi log gamma, which is exactly that. So I iterate the Veblen function according to the exponents of a Cantor normal form of gamma naught. And this is sharp. This is equal. So there are two parts of the proof here. One part is showing that you cannot do with any ordinal smaller than that. And in that case, we use the barriers generated by this system of fundamental sequences I described for gamma naught, for example. But I can show it if I move to a smaller ordinal using that system and the barriers generated by that system, I can find counterexamples. And the other one is showing that this is actually enough. So it's an upper bound that with this you can always find the right barrier of the right size that gives you what you need. So I'm not going into any detail because the proofs are quite long and complicated and with a lot of technical details, but I was trying to bring you to here. I mean, it takes already almost an hour, I guess, to get you here. So I think I'm stopping here.